Ever wonder how those self-driving cars, the ones everyone's talking about, actually see and navigate through traffic?
Or how about those crazy special effects in movies, like where time seems to slow down?
Exactly. Well, buckle up because today we're diving deep into the fascinating world of optical flow.
It's a computer vision technique that's basically teaching machines how to see and understand motion.
And we're getting all our insights from this really cool French technical paper. It's called, hold on, let me get this right. Flux optique, analyse du mouvement en vision par ordinateur.
I think you nailed it.
Well, get ready to have your mind blown because this stuff is seriously cool.
Yeah, it really is. We're basically talking about how computers can not just recognize objects in a video, but how those objects are moving.
Right, like understanding the motion itself.
Exactly. And that has huge implications for all sorts of things. I mean, we're talking robotics, special effects, you name it.
Okay, so let's break it down a bit. What exactly is optical flow?
At its core, it's all about how pixels move between frames in a video sequence.
Okay, so like tracking how those tiny dots on the screen change from one moment to the next.
You got it. But here's the thing, it's not actual 3D movement we're talking about.
What do you mean?
Well, it's more like a 2D projection of that movement, kind of like a shadow play of what's happening in the real world.
Okay, I think I get it. Like, we're seeing the effect of the movement, but not necessarily the movement itself in all its dimensions.
Precisely. It's like, imagine a tree swaying in the wind, right? We see those branches moving, those leaves rustling.
Yeah, I see it.
But optical flow isn't trying to capture every little detail of that movement in 3 dimensions.
So it's not like recreating a perfect 3D model of the tree and how it's moving.
Exactly. Instead, it's focusing on how the image of the tree changes on a 2D plane, like if you were tracing the outline of that tree on a piece of paper as it moved.
Uh-huh. That makes sense. So it's capturing the essence of the movement, how it's affecting the image, rather than the exact 3D position of every leaf and branch.
Exactly. And that's actually pretty powerful because it simplifies things a lot, computationally speaking.
So how does a computer actually do that? Like, what's the math, the magic behind these calculations?
Well, it's all based on this pretty straightforward assumption that a point's brightness, how bright a pixel is, stays pretty much the same from one frame to the next.
Makes sense. A leaf is still a leaf, even if it moves,
yeah.
right? The color doesn't magically change.
Right. So if a pixel changes position but keeps roughly the same brightness, the algorithm figures, hey, that's probably the same point, just in a different spot now.
Oh, I see. It's like connecting the dots, but with brightness instead of lines.
You got it. And by analyzing how these bright points shift, the algorithms can actually calculate the speed and direction of that movement.
That is so cool. So the paper talks about these two main ways to actually calculate optical flow: differential methods and correspondence methods.
Yeah.
Can you break those down for us? They sound a little, well, technical.
Sure, I can try. So differential methods, imagine you're watching a car race.
Okay, I'm picturing it.
You want to figure out how fast one of the cars is going. One way to do that is to look at how much its position changes over a really short period of time.
Right, and the more it changes in that tiny bit of time, the faster it's going.
Exactly. So differential methods, they kind of do the same thing, but with pixels. They look at how the brightness patterns change from one frame to the next.
And based on how much those patterns shift, they can figure out how fast each pixel is moving.
You got it. They're basically calculating those tiny pixel speeds to figure out the flow of the motion.
Cool. So that's differential methods. What about correspondence methods? Those sound even more complex.
They might sound more complex, but think of it like a matching game, where you have two pictures that are almost identical, but some things have moved around.
Yeah, like a spot the difference puzzle.
Exactly. So correspondence methods, they try to find the same groups of pixels in both images, like matching those puzzle pieces. And by seeing how those groups have shifted, they can figure out the overall motion.
So it's like following a cluster of pixels as they move from frame to frame, rather than just looking at individual pixel changes.
That's a great way to put it. It's like tracking a group of friends moving through a crowd.
I love that analogy.
Yeah.
So we've got these different methods for calculating optical flow, but how is this stuff actually used in the real world? I know you mentioned self-driving cars earlier.
Yeah, that's a prime example. Think about it. For a self-driving car to, not crash into things, it needs to understand how everything around it is moving.
Yeah, like other cars, pedestrians, cyclists, those wild animals that sometimes run across the road.
Exactly. And optical flow helps the car's computer see all that motion. It's a crucial part of how those vehicles perceive the world and make decisions, like when to brake, accelerate, or steer.
So it's not just about recognizing that there's a pedestrian crossing the road,
Mm.
but actually understanding how that pedestrian is moving and predicting where they'll be in the next second.
Precisely. It's all about predicting and reacting to motion in real time.
And this is probably a big deal for surveillance too, right?
Oh, absolutely. Security cameras are using optical flow to get way better at detecting motion. They can tell the difference between, say, a tree swaying in the wind and a person sneaking around.
That's pretty impressive. So it's
Yeah.
helping create more accurate security systems.
Yeah. And it can even help analyze security footage after the fact. Like, if something did happen, investigators can use optical flow to track movements and get a better understanding of what took place.
Wow, that's pretty powerful stuff.
It is. And it's not just serious applications either.
Wait, what do you mean?
Well, think about movies. Remember that bullet time effect I mentioned? The one from The Matrix?
Oh yeah, where everything slows down and the camera seems to circle around the action?
That's it. Optical flow is one of the key technologies behind that effect.
Really? How does that work?
It's pretty complex, but basically they're using optical flow to create extra frames between the original ones to make the action look super smooth, even in slow motion.
So they're like filling in the gaps between the real frames to create the illusion of continuous movement.
Exactly. And they're using the information from the optical flow to make sure those extra frames look realistic and match the flow of the action.
That is mind-blowing. So optical flow is helping to create some of those incredible visual effects we see in movies.
Yep. It's a key player behind the scenes. And this paper we're talking about, it even mentions applications in things like medicine and traffic analysis.
Seriously, what kind of things?
Well, in medicine, they're using it to analyze how tissues move.
That's interesting.
Yeah, it can be really helpful for diagnosing certain conditions or monitoring how well someone's healing after surgery.
That's pretty amazing.
And it's also used in eye tracking technology, which has tons of applications like understanding how people interact with websites or even helping people with disabilities control computers with their eyes.
Wow, I had no idea it was so versatile.
Yeah.
What about traffic analysis? How does optical flow fit in there?
Well, think about it. Traffic cameras are everywhere these days. And with optical flow, they can do way more than just record video. They can actually analyze how cars are moving, identify areas where traffic is slowing down.
Oh, wow. So they could use that information to optimize traffic light timing or even plan new roads?
Exactly. It's all about using the data to make traffic flow more smoothly and efficiently.
So we've covered a lot of ground here. We talked about how optical flow is calculated and all the amazing applications. But are there any particular algorithms, like the big names, that people might come across when they dive deeper into this?
Oh, for sure. There are a couple of algorithms that are like the rock stars of the optical flow world.
I love it. Hit me with the names.
Two that you'll hear a lot are Lucas-Kanade and Farnebäck.
Okay, Lucas-Kanade and Farnebäck. Got it. So what's so special about Lucas-Kanade?
It's known for being simple and efficient, which is always a good thing in computer science. It's great for tracking things like individual points or small features in an image.
So, like, if you wanted to track the movement of a ball in a video, Lucas-Kanade could handle that.
Exactly. It works best when the motion is pretty consistent in a small area.
Got it. So it's like a specialist for tracking small, well-defined movements. What about Farnbäck? What's its claim to fame?
Well, Farnbäck is a bit more sophisticated. It uses this cool mathematical trick called polynomial expansion to estimate the flow field over larger areas.
Polynomial expansion. Okay, you're losing me a bit.
Think of it this way. Imagine you have a bunch of scattered dots on a graph.
Okay, I'm picturing it.
Polynomial expansion is like trying to draw a smooth curve that fits through all those dots. Farnbäck uses this idea to estimate the overall motion in a region, even if it's pretty complex and not uniform.
Ah, so it's better at handling those situations where the movement isn't just one object moving in a straight line, but lots of things moving in different ways.
Exactly. It's like the all-star player for handling complex real-world motion.
Wow, this is incredible. I mean, who knew that something as seemingly simple as tracking how pixels move could be so powerful? We've gone from self-driving cars to movie magic and even medical breakthroughs.
Yeah, and we're just scratching the surface here. Optical flow is unlocking all sorts of possibilities in all kinds of fields.
So what's the one big thing you hope listeners take away from this deep dive?
I'd say the most important thing to remember is that optical flow isn't just some cool tech trick. It's really changing how we understand and interact with the world around us.
I agree. And who knows what other human senses computers will be able to replicate in the future? I mean, they could already see motion. What's next?
Yeah, the possibilities are truly endless, and that's pretty exciting to think about, don't you think?
Absolutely. Thanks for joining us today. It's been fascinating.
My pleasure.
And listeners, keep those minds curious, and we'll catch you in the next deep dive.